So expanding binomials. So 1 plus x to the power of n pretty much just means 1 plus x times 1 plus x times 1 plus x and so on n times. What we actually do when we expand out is we're taking one term out of each of the parentheses and multiplying them together. And then we have to do that every possible combination we can, and that comes up with all the terms. So effectively, if I wanted to get x cubed, I could take x out of the first one, 1 out of the second one, x out of the third one, 1 out of the next one, 1 out of the next one, 1 out of the next one, and so on and so on and so on, and then x out of the last one, and they would all multiply together and it would give x cubed. But that's just one way I could pick out the 3 x's. So the question is, how many different ways could I do that and end up with an answer of x cubed? Well, this comes back to our perms and cons. Because what we're really saying is, how many different ways can we choose 3 x's from n sets of parentheses? Well, that would be nc3. So there's a direct relationship between the binomial coefficients and combinations. So now let's have a look at expanding binomials out. So nck actually turns out to be the binomial coefficient in our expansion for 1 plus x to the power of k. What that means is we don't actually need to draw up Pascal's triangle. We can actually just calculate it out. Now, when we're dealing with binomials, the notation we use for combinations, it sort of looks like a column vector. Do you do column vectors in physics?
No.
Oh, okay, so it's more a mathematical thing. Well, later on we're going to look at vectors the next term. So don't confuse it with what we'll then see is called a column vector. We are talking about combinations here. So that's another way of writing nck. Right, so the expansion of 1 plus x to the power of n then becomes nc0 plus nc1x plus nc2x squared, and so on and so on and so on, up to the last term, ncn x to the n. Of course, that's just 1 plus x. That's very limiting just to have that. We could extend that through to say, well, instead of 1 and x, I could have a and b. Well, what happens with the terms? We'll start off with the first one, a. It'll be to the power of n. The powers of a then go down by 1. The powers of n go up by 1. Any particular term you pick, the two powers should add to give n. So if I want to expand out 2 plus 3x to the power of 4 then, I can say, well, okay, that's going to be 4c0, 2 to the 4. 4c1, powers of 2 going down by 1, so 2 cubed. Powers of 3x going up by 1, so 3x to the power of 1. 4c2, 2 squared, 3x squared. 4c3, 2, 3x cubed. 4c4, 3x to the power of 4. And fixing all that up, there we go. 16 plus 96x, 216x squared, 216x cubed, and 81x to the power of 4. So, we're going to have a look at the first 3 basic Pascal's triangle properties. Now, the first one here is that nck will equal n minus 1 ck minus 1 plus n minus 1 ck. That's basically the formula that allows you to create each row, because what it's really saying is, if I want to work out the number, I add the 2 numbers in the row before. So n minus 1 is the row before, I add the 2 together, and I'll get the nck. Let's do a proof of it. So 1 plus x to the power of n is 1 plus x times 1 plus x to the n minus 1. So the 1 plus x to the n minus 1, I now know I could expand out to be n minus 1 c0 plus n minus c1x, and so on and so on and so on. Somewhere in the middle, there'd be 2 terms. n minus 1 ck minus 1 x to the k minus 1, and n minus 1 ck x to the power of k. So somewhere in the middle, they'd be there. Now, I want to look at the coefficients of x to the power of k. That's all I'm interested in. So on the left-hand side, well, if I was to expand out 1 plus x to the n, only one of those terms would have x to the power of k, and it would be nck, x to the k. Now on the right-hand side, the 1 I would multiply with the n minus 1 ck x to the k, and the x I would multiply with the n minus 1 ck minus 1 x to the k minus 1. So on the right-hand side, we get those two coefficients added together. Well, they're both the coefficients of x to the power of k, therefore they must be equal. And so we have our proof for that particular relationship. Okay, the second one, NCK is equal to NCN minus k, and as I put there, that's basically the fact that the triangle is symmetrical. So the one on the end equals the one on the end, and they're always ones, of course. But then the second one equals the second last one, and the third one equals the third last one, and so on. And the last one there, again, that's a very basic property, but each row will start and finish with 1. So NC naught will equal NCN, and then they'll be equal to 1. Well, let's have a look at expanding parentheses in a bit more detail. We know a plus b squared is equal to a squared plus 2ab plus b squared. It's been drummed into our heads now for goodness knows how long. But let's look at it a different way. So a plus b squared. So let's think about all the different ways of writing two pronumerals using a and b. Well, there's basically three things I could have. I could have a squared, because that's two pronumerals, and there's both a's in this case, so a times a squared. I could have b squared, I could have ab. So how many ways could I arrange the two a's or the two b's? So a squared and b squared. So if I just had I said, look, here we go, AA. How many different ways could I arrange AA? One. Because both the letters are the same, there's the only thing I could have, AA. So I know I'm going to get one lot of a squared plus b squared. But how many different ways could I arrange one a and one b? Two. So I get 2 factorial times ab. And there is the a squared plus 2ab plus b squared. So if we think of it that way, now it opens up a lot more, because I could now expand out. A plus B plus C plus all the way up to N. Doesn't matter how many terms. It doesn't have to be a binomial now. It could be anything. But it's the same idea. I know, because I'm going to have two pronumerals, I could have the two of them being the same. So I could have A squared plus B squared plus C squared all the way up to N squared. But then I could also have all of those pairings. I could choose an A out of one and a B out of another. I could choose an A out of one or a C out of the other. Or I could go up to N, or I could have B times C, B times C. Any of those two. And then the question is, how many ways can I arrange those two objects? Well, 2 factorial, 2. So the expansion of A plus B plus C plus N all squared will always be each one of those squared plus twice all the possible pairings that you could have. Now, a plus b cubed then. So how many days? This time I'm going to write 3 pronumerals, because a plus b times a plus b times a plus b, I'm going to take one pronumeral out of each. So I'll end up with 3 pronumerals multiplied together. What are all the different things I could have? I could have an a cubed, I could have a b cubed. So if I pull a out of each one, or pull b out of each one. But I could pull a out of one and b out of 2 of them, so I could have ab squared. Or I could choose a out of 2 and b out of 1, and I would end up with a squared b. But that's all the possibilities I could have. So the question then becomes, how many ways could I arrange these objects? So how many ways could I arrange a? Well, there's only one. How many ways could I arrange an a b, and a b? 3 factorial on 2 factorial. So our expansion becomes a cubed plus b cubed plus 3 lots of a squared b plus ab squared. So again, I could extend that through. It doesn't have to be a binomial. So if I have a plus b plus c all cubed, so now I'm going to pull a pronumeral out of each one. What could I get? I could get a cubed, b cubed, c cubed, so they're all the same. I could get all the possible different ones there where I pour an A, for instance, out of one and a B out of the other 2, or it might be a C out of one B. So 2 of them the same, one different. But now there's a third possibility. I might just pull out an A out of one, a B out of another, and a C out of one. So how many ways could I arrange those objects? Well, the AAA, we know there's only one. The a squared b, well, it's still the same as the one before. It's going to be 3 factorial on 2 factorial. But what about the ABC? 3 factorial. Therefore, the expansion would be that. All right, let's have some fun now. Let's do it to the power of 4. So all the different ways. So I've now got a plus b times a plus b times a plus b times a plus b. I'm going to pull out a pronumeral out of each one. So I'm going to end up with 4 pronumerals. I could have all of them being the same. So that gives me a to the 4 plus b to the 4. I could have 3 of them being the same, one difference. So ab cubed or a cubed b. I could have 2 of them being the same and then the other 2 being the same. So a squared b squared. That covers every possibility. Question now becomes, how many ways can I arrange these objects? Well, a times a times a times a is only one way of doing that. A, b, 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 4 factorial on 3 factorial. A, b, b, 4 factorial on 2 factorial, 2 factorial. So the expansion of a plus b to the power of 4 would be that. A to the 4 plus b to the 4 plus 4 ab cubed plus a cubed b, and then you would have 6a squared b squared. What the heck? Let's go for a plus b plus c to the power of 4. So I've now got 3 I can choose from. I'm going to pull out 4 of them. I could have, all right, I could have them all being the same. There's the easy one. I could have 3 of them being the same and 1 different. Now there'd be 4 factorial, 3 factorial ways. We already determined that in the last one. I could also now have 1 being chosen twice and then the other 2 being chosen once. So you get a, b, c squared or a squared. Well, how many ways could I arrange a, b, c, c? 4 factorial on 2 factorial. I could also have the a squared b squared. Well, we already worked that one out, the last one. That ended up being 4 factorial, 2 factorial, 2 factorial. Is there any other possibility there I could have? No. I think that's about it, isn't it? So there you go. There is our expansion of a plus b plus c to the power of 4. Well, yeah, you could keep going. But anyway, 15b plays around with that. So say, with that expansion that I just did there, I don't know there's many questions on that, but I just thought it was a nice way of showing how there is a direct relationship between what we're doing with, Pascal's triangle and permutations and combinations.